Welcome back, everybody. This is Lecture 10, 4.2, Classifying Chemical Reactions and Predicting Products. Thought we'd start with another one of those amazing chemical reactions. Here we go. It's alive! It's alive! Question is, how many of you are going to go out and buy a cuttlefish and some soy sauce and try that at home? All right, here we are, back to our ebook, page 174. Again, this is 4.2, Classifying Chemical Changes and Predicting Products. I encourage you to give this warm-up a shot, to take a peek at this chart here, to acknowledge that there's 6 different types of reactions we'll be seeing in this section, and how it is we can identify them based on how many reactants and or products they have. Give this warm-up a go. Come back to me in a moment to see how you did. All right, so I got single replacement for one. We see an element and a compound forming a different compound and a different element. Single replacement. I got synthesis for number 2. I've got 2 substances forming a single substance. When there's just one product, it's always a synthesis reaction. I got combustion for number 3. This is a hydrocarbon. It's got hydrogen and carbon in it, reacting with oxygen to form carbon dioxide and water. 4 is, generally speaking, a double replacement reaction where 2 compounds form 2 new compounds. But because HCl is an acid and strontium hydroxide is a base, we'll learn that strong bases, there's also weak bases, strong bases always have hydroxide as their anion. Because this is an acid and a base, it's a special type of double replacement reaction called a neutralization. And then for 5, I got decomposition. Notice I'm using common abbreviations. SR for single replacement, S for synthesis, C for combustion, DR for double replacement, N for neutralization, and D for decomposition. Well, that list of 6 reaction types isn't a complete list, meaning there's other types of reactions out there. These will be the reaction types that you'll be held accountable for in this class. And the reason why we care about classifying a type of reaction is that it can help us predict the chemistry that's taking place, what's actually happening at the atomic level, and it can also help us predict what the products will be. And that's what the majority of this lecture is about, is by identifying the reaction type, being able to predict what the likely products will be. As we saw a bit ago in that warm-up chart, a synthesis reaction, or oftentimes called a combination reaction, involves 2 or more simple substances, which will either be elements or compounds, forming one complex substance. And really what's important about that definition is that when a single product is formed, when there's just one product, then it's a synthesis reaction. Synthesis reactions tend to be exothermic. They tend to release heat overall from the system into the surroundings. Reason why is if we imagine that we're forming a single substance, we're tending to either only form bonds or are tending to form more bonds than are broken. And if you have prior knowledge with bond formation, you may know that that results in an output of energy or release of energy. So the formation of the bonds in a synthesis reaction is what causes the reaction to be exothermic or to release energy overall. And we'll talk more about that in our next unit, thermochemistry. You can ignore this comment at the top here. It came from the publisher. I can't delete it. It's referring to a redox reaction, which is something that I'll teach you about later. So ignore that top comment. Down below this, though, we see that it says synthesis reactions may involve the combination of 2 elements to form a simple binary compound. A compound with just 2 elements in it, the 2 elements that were on the reactant side. This is the most basic type of synthesis reaction. These are the types of synthesis reactions that you will be more likely expected to be able to predict. We'll see in a bit, through this chart that I'll show you later, that there are more complex synthesis reactions, which are less likely to be confronted in this class. So here we see 2 examples of this basic type of synthesis reaction where the 2 reactants are just 2 elements. Top one is barium reacting with chlorine to form barium chloride. And the compound, as you might imagine, is comprised of just those 2 elements, barium and chlorine. Synthesis reactions will typically be a metal, barium in this case, and a nonmetal, chlorine in this case, forming an ionic compound. What's important about this is that when you write the formula for the product, you do so using the charges that those ions will assume when they're in an anionic compound. Barium, for example, forms a 2+ ion, and chloride forms a 1- ion. And that's why we get BaCl2. It's not because those happen to have been the subscripts on the reactant side. That's a coincidence. Rather, BaCl2 is coming from the charges that barium and chloride assume for that compound to be overall neutral. Down below, we see tin, another metal, reacting with oxygen to form tin oxide. Tricky one about this is that tin is one of those multivalent metals that can have more than one charge. Tin can be 2+ or 4+. So if I were to just give you tin and oxygen and ask you to predict the product, it would be hard for you to know whether it's tin 2 oxide or tin 4 oxide. So be okay that you could have written SNO or SNO2 if you thought it was tin 4. And from my perspective, either would be right. And then it's balanced, of course. Notice that once again, the formula for SNO isn't coming from the subscripts on the left. Rather, it's coming from the charge that in this case tin and oxide have, a 2+ and a 2- respectively. And we're seeing again oxygen being reflected as a diatomic molecule. Oxygen is always O2. Chlorine is another of those diatomic molecules. It's Cl2. And I'll remind you what all 7 of them are in a bit. As I mentioned a bit ago, the most basic synthesis reactions are 2 elements forming a binary compound with just 2 elements in it, typically a metal and a nonmetal. Well, some synthesis reactions involve the combination of 2 compounds to form a more complex, simple compound. And if I click on this comment, which I did put in there, it's telling us that we should see page 177, for example. So we'll go to that page in a little bit to see the types of compounds that can form a more complex compound. And these are the trickier synthesis reactions. Again, before we look at those trickier synthesis reactions and move on to decomp reactions, I'd like to do just one of these with you. Here's calcium and nitrogen. We assume this is a synthesis reaction because it's just 2 elements, and we put calcium and nitrogen together in an ionic compound to form the product. It'll be called calcium nitrate. Well, calcium, when it's an ion, is always 2+. Nitrogen, when it's an ion, is always 3-. And I neglected to remember that nitrogen is also always diatomic, so I need to put a 2 in there. All right, well, when a 2+ and a 3- ion combine, it'll be Ca3 and 2, nitride being 3-, calcium being 2+. And then to balance this, I'm going to need to put a 3 in front of calcium. It's a coincidence, once again, that nitrogen has the same subscript on the reactant side as product side. It's a 2 here because nitrogen's diatomic. It's a 2 here because of the charge of calcium being 2+. So there's a synthesis reaction, once again. So I've scrolled down. I'm on page 167 of the textbook, or page 175 of the ebook, looking at decomposition reactions. A decomposition reaction involves a complex compound, a single compound, most importantly. The reactant will be a single compound being broken down into 2 or more simpler substances. A decomp reaction, our book says, is really just the opposite of a synthesis reaction. Whereas in a synthesis reaction, there is a single product. In a decomp reaction, there's always a single reactant. They're the opposite of each other. That's true from an energy standpoint as well, whereas synthesis reactions are typically exothermic because more bonds are typically formed than are broken, and therefore energy is overall released. Decomp reactions are typically endothermic. To break those bonds, energy is required in a decomp reaction. Down here, we see an example of the simple type of decomp reaction where the reactant, the single reactant, which is a hallmark of decomp, is a binary compound. There's just 2 elements in it. So the only option would be, if this reaction took place, would be for those elements to break apart, for the bond between aluminum and oxide to break, and to form aluminum and oxygen. Oxygen, again, is diatomic. That's why we see it as O2. And there's some phases indicated in there, and you can see it's balanced. This is probably a good time to make sure that you're all familiar with which of the elements in nature are always diatomic. There's 7 of them. There's 7 elements in nature that are always diatomic. Oxygen, we've already seen as O2. Chlorine is Cl2. Well, there's 5 others. One of those is hydrogen. Hydrogen's always H2. Another of them is nitrogen. Over there, element 7. Nitrogen is N2. Oxygen we already know is diatomic. Fluorine is diatomic. Chlorine underneath fluorine is diatomic, and so are bromine and iodine. There's a couple of mnemonics you can use to remember these. One of them is Hunkelbrief. H-O, honk. Nitrogen, chlorine, bromine, iodine, and fluorine. Hunkelbrief, if you like it, can help you remember the diatomics. Another one is that there are 7 diatomic elements, and except for hydrogen, one could say they start with element 7 on the periodic table. Nitrogen is 7. And if we move through the periodic table, NOFClBri, we see that that is a 7. There's 7 of them. They start with element 7, and they make the number 7 on the periodic table, NOFClBri, including hydrogen. So Hunkelbrief or 777, or memorizing these will be important. I've flipped my page. I'm on 176, the ebook, and I've got an example decomp reaction in the upper left-hand corner. This is aluminum fluoride, AlF3, that would undergo decomposition because the reactant is a single compound, and this again is a binary compound, the only option being for it to decompose into its individual elements. Well, aluminum is just going to be Al, it's not diatomic, but fluorine is diatomic, so it will be F2. So the products will be aluminum and fluorine, and when I balance this, I'm going to need to put a 2 in front of AlF3, a 3 in front of fluorine, and then a 2 in front of aluminum here. Same page here. This is that chart I referred to earlier, which will be showing us how to deal with the more complex decomposition and synthesis reactions. But before we look at those, I want to acknowledge that this bottom row describes what we've been looking at, which are these more straightforward decomp or synthesis reactions, where either the product is a binary compound, there's just 2 elements in it, a synthesis reaction with just 2 elements forms a binary product, or in reverse, the reactant is a single binary compound and it decomposes into just 2 elements. And like we heard earlier, synthesis and decomp reactions are the reverse of each other. So when we have a metal and a nonmetal forming a binary salt, that's synthesis. And in reverse, when a binary salt decomposes into a metal and a nonmetal, that's decomposition. So it's these top 3 rows that we're going to talk through now that are the more complex decomp or synthesis reactions. If this next section feels overwhelming or confusing to you, or it seems like you just can't see the pattern, or predicting these products will be difficult for you, that's going to be okay. While I want you to be familiar with the patterns in these types of reactions, it's not going to be an important part of this class. You'll never see one of these trickier decomp or synthesis reactions on one of our tests in here, and I have never seen one on an actual AP test. So don't worry again if this next little section is a bit tricky, because it is. So we're looking at the top row, where a nonmetal oxide and water through a synthesis reaction can form an acid, or in reverse, if the reactant were an acid, through decomposition, it would decompose back into a nonmetal oxide and water. Again, synthesis and decomp being the opposite of each other. So here's an example. Sulfur trioxide is a nonmetal oxide. Sulfur is a nonmetal and oxygen is oxide. So this is a nonmetal oxide reacting with water. It forms an acid. Remember, acids always have hydrogen as their cation. So we know that that will be the positive ion. The question is, what will the negative ion be? Well, it's going to be polyatomic. It's going to be a polyatomic ion, and it will have sulfur and oxygen in it. There's a couple options. It could be sulfite, SO3. It could be sulfate, SO4. We'll learn later what the guaranteed likely one is, but for now, just use logic or intuition, if such a thing exists. In this case, SO4 is the more likely candidate for the polyatomic ion because the 1 oxygen from water and the 3 oxygens from SO3 can form sulfate. So we put hydrogen as our cation. Knowing sulfate is a 2- ion, SO4 is a 2- ion, we'll need 2 hydrogens to be paired with sulfate. And there is the synthesis reaction between a nonmetal oxide and water, forming an acid, sulfuric acid. We're looking now at the second row, which suggests that a metal oxide and water in a synthesis reaction form a base. And in reverse, a base as the single reactant through a decomp reaction will form a metal oxide and water. Off to the left here, we see an example of a metal oxide, calcium being a metal, oxygen being oxide, and water that will apparently form a base. Well, you heard me a bit ago say that strong bases, there's weak bases, we'll learn about them later, strong bases always have hydroxide as the anion. So the anion will be hydroxide this time, and the cation will be the metal. So we're going to form calcium hydroxide. When a metal oxide and water react, they form a base, or they form the metal hydroxide that comes from the metal that was originally paired with oxide. So we need to form calcium hydroxide. Calcium is a 2+, hydroxide is a 1-. So with charge cancellation, we're going to get Ca parentheses OH sub 2. And it happens to be that this is already balanced, but if it weren't, we would need to balance it at this point. We're now down to row 3, looking at the fact that nonmetal oxides and metal oxides in a synthesis reaction form a complex or ternary salt. That's another term for an ionic compound whose anion is a polyatomic ion. In reverse, a complex ternary salt or an ionic compound whose anion is a polyatomic ion through decomp reactions form nonmetal oxides and metal oxides. Again, synthesis and decomp being backward from each other or reverse. So here we see a nonmetal oxide, sulfur being a nonmetal oxide, and a metal oxide, sodium being a metal, reacting. And they're going to form a single compound. The metal, sodium, will be the cation. So the metal in the metal oxide will always be the cation, and the anion, you heard me a bit ago say, will be a polyatomic ion. It'll be one with sulfur and oxygen in it. Kind of like the first example I did, there's a couple options, sulfide or sulfate. Whichever one seems to make most sense at this point, pick. And that would be sulfate once again, because the 1 oxygen from sodium oxide and the 3 from sulfur trioxide can form sulfate, SO4. So we need to form sodium sulfate. Sodium is a 1+ ion, sulfate's a 2-. So our compound in the end will be Na2SO4. And it is balanced already. I'll do one more with you. We're starting this time with a base, a single compound. And that's going to indicate that it's a decomp reaction. Again, this is a base because hydroxide is the anion, strong base. So we need to decompose this into a metal oxide and water. Well, the metal will be aluminum still. O is oxide, and then we form water. So I need to form aluminum oxide and water. Aluminum is 3+, oxide's 2-, so I'm going to get Al2O3. Ooh, that's a nice O. And water, of course, is H2O. To balance this, I'm going to need to put a 2 in front of aluminum. Oh boy, running out of room. And I think, to finish her off, yep, we just need a 3 in front of water. So that was a decomp reaction, starting with a base, forming a metal oxide, aluminum oxide, and water. Again, these can feel pretty tricky and intimidating. You'll have a chance to practice these with homework later. If this is a skill that you never acquire, you'll be highly functional in life, I promise, and in this class. But it is this last row that everybody should be comfortable with. When the compound has just 2 elements in it, it breaks apart into those 2 elements. So too will 2 elements form just a simple binary salt. We are now onto our third reaction type, combustion reactions, and this will be the last reaction type we do before the first part of this lecture is done. So a combustion reaction involves the reaction of a hydrocarbon, which we saw in the warm-up, just hydrogen or carbon in it, or a carbohydrate made of hydrogen, carbon, and oxygen, along with oxygen gas to produce carbon dioxide and water. Hydrocarbons or carbohydrates, when they react with oxygen, always produce carbon dioxide and water. That's a really important biologic reaction as well. All the cellular respiration we do on our proteins, carbohydrates, and fats are all combustion reactions happening on a very small scale. Well, they release tons of energy, which is why our bodies take advantage of those biomolecules to get energy out of them. They are highly exothermic reactions, the combustion reactions of carbohydrates and hydrocarbons. Down below, we see an example of each of those. This is a hydrocarbon. It's octane, and it's reacting with oxygen to produce, as we would expect, carbon dioxide and water. And notice those coefficients are quite big for us to have balanced that. Down below is a carbohydrate. This is glucose reacting with oxygen to form, again, carbon dioxide and water. So we're now going to flip the page. We're now on page 177 of the ebook, 169 of the textbook. And I invite you to try this quick check at the top of this page. Pause this video, come back in a moment, and see how you did. And that will conclude this first part of Lecture 10. The defining feature of 1 is that there is a single product. A single compound is the product. And anytime we say a single compound is the product, we know it's synthesis. Furthermore, this is a metal oxide and water forming an acid. So this one is synthesis, S for synthesis. Here we see the two products being carbon dioxide and water. That will be characteristic of a combustion reaction, further substantiated by the hydrocarbon reacting with oxygen. So this is combustion. Finally, we see a single reactant, hallmark of a synthesis reaction. Furthermore, this is an acid, carbonic acid, decomposing into water and the corresponding nonmetal oxide, the nonmetal that was in the polyatomic ion along with oxide. So this one is decomp. That's it, folks. Part 2 coming your way next. Enjoy the rest of your day. Work hard, be kind. Do unto others as you want done unto yourself.